Good morning, my dear students. कैसे हो? Am I audible and visible to all of you? I hope I am audible and visible to all of you. Yeah, internet connection is going on, and I have put the right link. Yes, I am audible and visible. देखूं जरा visible हूं या audible हूं या नहीं. Audible का भी check कर लेता हूं. Am I? हाँ, audible हूं मैं. तो चलिए आ जाइए, सबके सब आ गए हो आप? Okay, fine. Ananya, are you there? Because you have asked a question yesterday in the WhatsApp group. You have asked a question. Let me answer that question. Hello Prerna, hello Tirthraj, Naruto, Piyush, Sagar. Welcome Sagar. I believe you are first time here. So, Ananya, should we start with Ananya's question? Ananya का जो question था, let us start with that particular question first. उसको doubt को solve कर लेते हैं. And oh, Ananya is here. ये क्या हो गया इसको? वो जो डायग्राम्स है ना, वो बड़े मुश्किल से बनते हैं, इसलिए थोड़ी सी प्रॉब्लम होती है. ये डायग्राम था ना? Prerna, sir, if the thermal energy is high, then the attractive energy might not be strong, right? बेटा प्रेरणा ये नहीं है कि अट्रैक्टिव एनर्जी थर्मल एनर्जी से चेंज हो जाती है. अट्रैक्टिव एनर्जी रिमेन्स द सेम as before. The only thing is thermal energy overpowers it. It's something like, let's say you have a thread, you are straining it. That doesn't mean that the thread attractive force becomes less. Your energy becomes more, and that is why the thread breaks. Same is with the solid, liquid, and gas. When you provide thermal energy, that is, you increase the temperature, it increases the thermal energy, which overcomes the attractive force. It is not that attractive force becomes less. Okay. Now, Ananya, let me answer your question. Here we have this particular atom. Here we're talking about this particular atom. Is it clear? Now, if we talk about this particular atom, then in that case, you can see here this part. Yeah. This, 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 and this are equidistant from this particular part. ये इससे equidistant है सारे के सारे. Same is here, these four. Okay. Same is here, these four. Okay. Now, your question was a peculiar one, which says that, sir, अगर एक क्यूब में coordination 8 है तो दो क्यूब में 12 कैसे हो गया? The answer is एक क्यूब का कोई मीनिंग ही नहीं है. When we are talking about the solid state, we are talking about an infinite arrangement. Clear? I have taken two cubes because there are only the particles from two cubes are attached to this particular particle. That is why I took two cubes. I could have 10 cubes. I could have 20 cubes. I could have taken 1,000 cubes. Is that clear? So that is why the coordination number in a face-centered cubic arrangement for every particle is 12. It is not about one cube, two cube, or three cubes. Is it clear, Ananya? Anyone has any confusion with that? Anyone has any confusion in yesterday's any topic? And I sincerely believe if you have made the notes, then only you will realize whether you have understood it or not. If you have not made the notes, you will feel, हाँ आता है, सब कुछ आता है. जब notes लिखते हो ना, जब लिखते हो, तब पता चलता है कि कितना आता है, कितना नहीं आता. Okay? So let's begin over with today's lecture. Sir, after watching a lecture of solid state, I had some confusion. Therefore, I watched Baiju's app videos on solid state and my concept becomes crystal clear. Okay, Piyush? You are commenting, complimenting, or you are degrading me? You want to say that those things are required? अजीब लग रहा है यार. क्या कंफ्यूजन रहा मेरे लेक्चर के बाद? If you had any confusion in my lecture, you should have asked me. That would have been better. तुम इस तरीके से मेरी इंसुलेट कर रहे हो. Okay, now, so that's what we have a solid state, and we are talking about the defects in solid. Clear? But we have to talk a little bit more about, before we talk about the defects, we have to talk about certain things more, certain important parts more. Okay. Now, what are those certain important parts? Let's discuss about it. Okay. So this is Elixir dropper batch for NEET UG 2024, and it's going to start from 16th August onwards. We have the in-depth analysis of PYQ, revision classes, exam strategies, mentor-mentee program, and botany 6:30 to 7:30 p.m., chemistry 7:30 to 9 p.m. Certain topics have been written at 7:31 p.m. I don't know how much difference 1 minute is going to make. A difference is a difference only if it makes a difference. But if it doesn't make a difference, forget it. So here we have an Elixir dropper batch. You can already enroll in it and you can start with it. Clear? You can use the code WS Live or you can use the code AV Live. So you can use the code. What happened? AVLIVE. Okay, it is in capital. AVLIVE. आप capital लिखो, small लिखो, कोई फर्क नहीं पड़ता. You are going to get this much discount. Okay. Now this discount is up to 31st of July, so it is better you join now. Okay. So that's me, and you know that it's me. Fine. Now we are going to talk about the three-dimensional close packing from two-dimensional hexagonal close packed structures. Now let's begin over with it. Okay. Now three-dimensional close packed structure can be generated by placing layer over one over the other. Now let's see how we are going to create the three-dimensional hexagonal layers. As you would be knowing, here we have okay, मैंने इसे कॉपी कर लिया क्या? Right. So here we have a circle. Okay. We paste it. We paste it. Okay. Now this is a hexagonal layer. Clear? So this is a hexagonal layer. Now what I do is I copy this entire layer and I paste it. Now what I do is I place it right on top of it and I just change the color of it. What color should I make? Can you see that layer? I have placed the layer right on top of it. Now what I find is there are two types of toppings. There are two types of toppings and how I change the topics, let's see. What are the two types of toppings? Here, here what I find is that this is 1, 2, and 3, and this particular yellow one is right on top of these three. So it is 1, 2, and 3, and the fourth one is right on top of these three. Is this clear? Yellow is not better. Yellow is just to distinguish between white and yellow. Okay. Now this particular position is called a tetrahedral void. Clear? This particular position is called a tetrahedral void. Now, let us see another one. Here we have 1, here we have 2, and here we have third one. Clear? And over that we have got the yellow ones, 1, 2, and 3. Now what I find is that I have a triangle like this, and another triangle is on top of it like this. And here inside there is a gap. This is the gap. Can you see it? Now this particular gap, which is formed by the two twisted triangles, that is, we have three atoms here. We have three atoms, 1, 2, 3, and another three atoms on top of it, like 1, 2, and 3. Now here in between, this is called the octahedral void. Is it clear? So this is what we have as two layers. Fine. Now, once we have made the two layers, do you know I can make a third layer on top of it? Clear? I can have two layers and I can create a third layer on top of it. Now, how do I do it? What I do is I again get this particular thing. So I again copy it. I can place it like this and I can make it as yellow. Clear? Fine. Now, what I can do in addition to this is I take another layer. Okay, I change the color of this layer initially itself. What should I make it? Okay, orange. Now I can place this particular layer right on top of the first layer. This is one possibility that I can do. Or there is another possibility that I can place it in a little different way, like this. In the gaps of the second layer. They are all same, Ankan. They can't be different. They are all same arrangement. All are the same atoms. See? So there are two ways of placing the third layer on top of the second layer. There are two ways. One, I can place this layer exactly as a first layer. And second, I can shift it a bit and I can place it like this. Okay, on top of the third layer. Yes, Ankan, the diagram is confusing. I agree with it. Okay, see, here I have the two layers. Second layer is clear that I have placed the second layer in the gaps of the first layer. Second layer is clear. Now I want to place the third layer. And there are two ways of placing the third layer. Either I can place it exactly like the first layer, or I can shift it a bit and I can place it in the gaps of the second layer. Okay. Now, if I place it in the first layer as it is going to be an AB-AB arrangement. Okay. So, this is what we know as the AB, AB, AB arrangement. It's going to be 1, 2, 1, 2, 1, 2. The same kind of arrangement is going to be. But when I talk about this particular arrangement, it is A, B, C arrangement. So there are two ways of arranging the hexagonal layers over each other. Now, if I want to put the third arrangement, third layer, if I want to put the third layer, whatever I may do, it is going to be either the first, like the third layer, or the second layer, or the first layer. So the third layer is bound to be the same as the first layer. So I can either have ABC arrangement or there is no other arrangement possible. There isn't any arrangement possible. If I try to make it anyway, if I shift it, there isn't going to be any other arrangement. It's going to be either A, B, or C. So it is more like ABC arrangement and it goes on. Is it clear? So there are two ways of arranging hexagonal layers over each other. Either AB arrangement or it is ABC arrangement. Am I clear with that? I know this is confusing. That is why I'm doing it so slowly. Okay. So there is either AB arrangement or it is ABC arrangement. Is this clear? Tirthraj, what happened? Why are you so confused? See, I believe my diagram was better than this. Now we have a series of tetrahedral and octahedral voids. Whether we have ABC arrangement or we have AB arrangement, the tetrahedral and octahedral voids are going to be the same. And further, the packing also is going to be the same. The efficiency and everything is going to be the same. Coordination, number, contribution, everything remains the same. The only is ABC arrangement and AB arrangement. Is this clear? So here what we can see is we have this kind of an arrangement. Clear? If you see, what we find is that if we have a hexagon, we are going to have a triangle on top of it. A hexagon will have a triangle on top of it, and again we are going to have a hexagon. Now this is AB arrangement. This is AB arrangement. Ankan, it's my wish. I can place the third layer as I like. One way is to place it the same way as the first layer. So it is going to become AB arrangement because the third layer is going to be same as the first layer. Or it could be I place it differently and I make it a C layer. So the fourth layer is going to be identical to the first layer. So there are two ways. Either the third layer is same as the first or the fourth layer is same as the first. So if the fourth layer is same as the first, it is A, B, C arrangement. If the third layer is same as the first, it is A, B, A, B, A, B arrangement. Clear? Now, A, B, A, B arrangement of the hexagonal layers is called the hexagonal closest packing. The hexagonal closest packing. The AB arrangement of the particles. And this thing which we have got is called hexagonal unit cell. So this is the hexagonal unit cell. Fine. I know this is a confusing part. No problems. Now, when we talk about this solid state, this hexagonal unit cell, I believe this arrangement you have seen many times. अभी देखिए ये arrangement. दिख रही है? अगर सुबह नाश्ता करके नहीं बैठे हैं तो सर क्या कर रहे हो, है ना? Can you see? Here is going to be a triangle. This is going to be a triangle, and this one is on the top of the triangle, forming a tetrahedral voids. Clear? Now, this hexagonal arrangement is not something unique. It is absolutely common. It's the most versatile, it's the most common arrangement that you are going to see anywhere. Anywhere. Okay. Now, this is AB arrangement, as you can very well see, and this is the ABC arrangement. This one is ABC. Now, C1 would be the twisted triangle. Okay. When we talk about the ABC arrangement, its ABC arrangement is something like we have a triangle. We have on top of it the hexagon. And then we have an inverted triangle. So this is what we have as the ABC arrangement. Naruto, now you cannot get it in your stomach, so I believe अब तुम्हें arrangement दिखाई दे रही है ना? Now I believe you are able to appreciate the arrangement rather than the mithai. Okay, so this is what we have as AB arrangement of the particle and the ABC arrangement of the particle. This is AB arrangement. Is it visible perfectly? I'm not able to find it out. I have that arrangement here lying somewhere. Arrangement कहाँ गई? Okay. Now, this is again ABAB arrangement. This is another way of writing it. I hope it is getting visible and it is getting clear. अगर एक डायग्राम क्लियर नहीं होता तो दूसरा देख लो, दूसरा नहीं क्लियर होता तो तीसरा देख लो, किसी भी तरीके से आप देख लो, बस समझ में आना चाहिए. Okay? Is it getting very clear? And whoever's not liked it, go ahead and like it. Is this clear? यार मैंने थोड़े से और ज्यादा लड्डू रखे थे, बाकी लड्डू कहाँ चले गए? ओह, ये लड्डू तो मिस हो गया. हाँ भाई. आई बिलीव इस समय लड्डू नहीं दिखाई हो रहे वो दे रहे होंगे. कैन यू सी द हेक्सागन? अ परफेक्टली फॉर्म्ड हेक्सागन. गुड मॉर्निंग संतीराम सरकार. So can you see the hexagonally close packing here? मन कर रहा होगा क्या टॉर्चर कर रहा है यार. Is it visible? The hexagonal arrangement. So if you have any kind of doubts, you can just visit any of the halwai and you can actually see hexagonal arrangement in the various mithai placed there. The hexagonal arrangement, the ABAB arrangement, and the ABC arrangement. All kind of arrangement would be visible right there. So please remember, why is it this kind of an arrangement? This kind of an arrangement is right there because this is the most stable arrangement. This is the most efficient arrangement. Is this clear? So this is the most efficient arrangement that you can see through the hexagonal arrangement. Clear? Now this is the hexagonal unit cell. This is the hexagonal unit cell. Now please remember this particular atom. This particular atom has a contribution of 1 by 6. This atom has a contribution of 1. This atom has a contribution of 1 by 2. So if anybody asks you what is the total contribution of the particles in the hexagonal unit cell, it will come out to be 1 by 6 into 12 plus 1 by 2 into 2 plus 1 into 3. The total value will come out to be 6. Is this clear? And now, one little thing I would like to tell you, that when we talk about the ABC arrangement, this is AB, AB arrangement, AB, AB arrangement. Now, this is ABC arrangement. The ABC arrangement actually is the face-centered cubic structure. That is why hexagonal unit cell and the face-centered cubic cell, they have exactly the same efficiency. They have exactly the same coordination number, and both are equally stable. Is this clear? So this is the hexagonal arrangement. हाँ सॉलिड स्टेट की स्पेशल क्लास होगी आज. Is that clear? So this is hexagonal closed packed structure and the face centered cubic structure. Okay. Now these are the arrangements which we have. So many arrangements, so many things. Now one thing you need to understand, one thing very, very clear about the octahedral and the tetrahedral voids. Clear? Just a minute. Now a little about the face centered cubic arrangement. Little about the face centered cubic arrangement. Here, what we have talked about the face centered cubic arrangement, the face diagonal is 4 times the edge length. Okay. Could we just solve this particular question? An element has a body-centered cubic arrangement with cell edge of 288 picometers. The density of the element is 7.2 gram per centimeter cube. How many atoms are present in 208 grams of the element? And this question was asked in the NEET examination. Okay, solve it. Now, this is a solved example of NCERT. Now, this is its solution. Read through it. Anything you want to ask here? पिकोमीटर्स को कन्वर्ट करने में 1 picometer is equal to 10 raised to power minus 12 meters. Okay, it is equal to 10 raised to power minus 10 centimeters. Is it okay? 1 angstrom is equal to 10 raised to power minus 10 meters, which is equal to 10 raised to power minus 8 centimeter. Is that clear? Any confusions here? कोई पॉइंट कंफ्यूजन? Now here we have another question. Just go through it. This is again example 1.4 of NCRT. Example 1.4 of NCRT. If you have the NCRT book, fine enough. If you don't have the NCRT book, this is the example. Today itself, we are going to read through the NCRT also of the solid state. This is the first part. Now, this question was asked in again NEET examination. So, solid state questions mostly are from the solved examples of NCERT. So, how we are going to solve it? X-ray diffraction studies that copper crystallizes in the FCC unit cell with cell edge of this much. In a separate experiment, copper is determined to have a density of this. So we get the formula as a density is equal to 4 into molar mass of the copper divided by the Avogadro's number into the edge cube. So this is going to be 3.608 into 10 raised to power minus 8 whole cube. Is that clear? So this is what you are supposed to calculate. Now this calculation cannot be done in the examination. This is not possible. Not possible at all. You won't be able to do the calculation in the examination. So what you can only do is you can just do the questions in NCRT, and that you can just simply put the answer right there. Is that clear? Another question. Just go through this question again. Anybody who has not liked the session, go ahead and like the session. हाँ जी, ये भी एनसीईआरटी पे है. Atomic mass is given as 109.9, 107.9 U, which can consider as 108 U. Not a problem. This much is accepted. Okay. Edge length is given. Now density is required. Now CCP lattice is the FCC lattice, face-centered cubic arrangement. So here again, Z is equal to 4. Okay. This is the solution. Is this clear? Now we are going to talk about the ionic arrangements. So let's have the ionic arrangements and we understand about that. Is this clear? Now, one thing we talk about. Now we talk about something called the ionic lattices. Ionic lattices की important बात ये है. The thing about the ionic lattices is that in the case of ionic lattices, the single kind of particle is not there. We have at least two types of particles because we are going to have the cation and anion at the least. We can actually have two cations or two anions also, but at least one cation and one anion will always be there in the ionic lattice. So at least two type of particles will always be there in the ionic lattice. Okay. Fine. So what we need to do is we have to modify the Bravais lattices a bit. We have to make a little modification in it. So these simple arrangements could be the arrangement of the molecular substances, could be of the elements, could be of the metals, but these can't be of the ionic substance ever. Now, to have the substance arrangement of having two or more kind of particles, now what we do is we make the entire Bravais lattice of one kind of particles. Okay. Now, let us say we have to make the arrangement. What we will do is we'll make the arrangement of the largest particles first. And it is always done like whenever you are packing something, you pack the largest particles first, and then you place the small particles in the voids, in the gaps. It is a normal phenomenon, and this phenomenon is found in the nature as well. In the case of nature, also, we arrange the largest particle the first, and then we place the small particles in the gaps. Is it okay? So, now if we are talking about the large particles, we have the cation and anion. Most often, the anion is the large particle. So what we do is we make the entire arrangement of the anion and we place the cation in the voids of the anion. Is it clear? So this is what we have as the arrangement. But now we talk about the size of the void. Size. Please understand, void is a continuous structure. It does not have any specific shape. Maybe it has a shape, but that shape is not a sphere. So when we talk about the size of the void, it is not actual volume of the void. It is the radius or the diameter of the sphere which fits in the void. So that is what we term as the size of the void. And one very, very important thing, size of the void is not just a number. Clear? Okay. The void has a range. It expands. It is something like we have a pajama with elastic in it or nara in it. Now, when we talk about that pajama has a minimum and a maximum size. Fine. So the person who fits in that pajama, please remember that pajama is a void. And the person who fits in that void is the particle which we are talking about, the cation or the anion. The person who fits in the pajama, that size could vary and pajama would expand or contract according to the person. But of course, there is a minimum and a maximum range. If you put elastic in it, there is a minimum value. Beyond that, goes down. And there is a maximum value, it cannot expand beyond that. Similarly, a void also has a minimum and maximum. So void always has a range. And whenever we represent the range of the size, we do not give the exact value of the size. We give the ratio. Okay. So ratio of the void is the size of the void divided by the size of particle making the arrangement. Okay, so that is always the ratio. Most often the size of the void is radius of the cation and the size of the particle, not between the structure, beta, within the structure. Voids are the empty spaces within the structure. Clear? Not between the structure. Okay, and the size of the particle making the arrangement is most often R minus. So when we talk about the ratio, we always have the ratio of R plus upon R minus. This is what we talk about the radius ratio. Is this clear? So this is what we term as the radius ratio. Okay. Now the size of the void depends on two factors. First of all, it depends on the size of the sphere making the arrangement. Larger the size of the ion, larger would be the void. Quite obviously, if we put the footballs, the gap between the footballs within the structure of the footballs is also going to be large. If I take it cricket balls, the size is going to become smaller. If I take the tennis balls, lawn tennis balls, the table tennis balls, the size is further going to decrease. Okay. And then we talk about the coordination number of the void. That is number of lattice points required to or surrounding the voids. Okay, how many lattice points are there which create the void? Okay, is it clear? So more are the particles creating the void, larger would be the size of the particle, as you can very well see here. Here, when we talk about this particular void, this void, you can see here, this particular void. Here it is one, two, three particles. So this is the size of the void. Now, if I talk about this one, can you see that? Here, there are 4 points making the void, and the size of the void is so big. So if I make the coordination number, now here we can see the inside the gap here. Here the 8 particles make the void. This is called the cubic void. So you can see how large the void turns out to be. So more are the lattice points required to create the void. That is, more is the coordination number of the void, the larger is the size of the void. And further, voids are named by the coordination number. So voids are classified as the coordination number. If we say tetrahedral void, the coordination number is 4 and it's going to form the structure of a tetrahedron. Square void, so square planar void, that will be 4 particles in the square planar arrangement and the void between them. Octahedral void, so it is going to have a coordination number of 6 and it's going to have a particle size of the octahedron, center of the octahedron. So that is what we have as the coordination numbers. Is this clear? So that is what we have as the coordination number and the various voids. Any kind of doubts, anybody? So size of the void is represented as a ratio with the size of the particle making the arrangement. More the number of ions containing a given void, larger it is. Clear? And as I told you that anion is mostly the large ion. So we generally make the arrangement for the anion and place the cation in the void. Is this clear? Any confusions? Okay, so here we are representing the range as r plus upon r. Read through it. Whenever you talk about the size of the void, think of the pajama with the elastic in it. Okay. Now this is the radius ratio rule table. Now this table is not present in NCRT. Maybe many of the books doesn't have it. So just note it down. As you can very well see that octahedral and square planar have the same size. Whereas tetrahedral and square planar have the same coordination. Actually, the square planar void is a octahedral void from which the top and the bottom two particles have been removed and a square has been left in between. So that is what we have as a square planar void. So square planar void and octahedral void have the same size, but the square planar has the coordination of 4. Okay. Body centered void is also termed as the cubic void. Is this clear? Okay. ओके ऋतिक मार्केट से लेट हो गए पर क्यों गए थे मार्केट आपको पता था ना 10 बजे क्लास है बेटा ये बातें ना इस क्लास में मत किया करो कि मेरा नाम लीजिए अगर आप अब किसी ने भी बोला ना मेरा नाम लीजिए आई जस्ट ब्लॉक द पर्सन यू आर हेयर टू अटेंड द क्लास not to get your name announced. Now we are going to consider some simple arrangement. Okay. Now, one thing. The body center of a simple cubic unit cell is a body center void or a cubic void. Okay. Now we are going to talk about the cubic arrangement. Simple cubic arrangement. Is it clear? Okay. And now we are going to talk about some very important factors, and now I am going to teach you by writing it. Let's consider a cube. Okay. This is the cube. Now here we have the particles on the corners. Okay. So this is a simple cubic unit cell. This is a simple cubic unit cell. Whether you are my ex स्टूडेंट or not, but still ये काम नहीं होगा. आप पढ़ाई कीजिए, आपके अगर कोई बात होगी, कोई क्वेश्चन होगा तो फाइन इनफ, आई विल एड्रेस यू बाय द नेम, लेकिन ये चीज नहीं चलेगी. ओके. Now what I do is I place a particle right here. Now you can see the coordination number is equal to 8. So this is a body centered void. This is a body centered void. Okay. Fine enough, you are in AIMS, perfect, no problems. But that doesn't make a difference here. This is not the way to ask me to take your name. And if you are in AIMS, I would sincerely request you to send me your scorecard. Send me your scorecard. And then we are gonna not only uh, take your name, but we are going to also arrange an interview for you. Send me your scorecard. Okay? So let's get along further. So the coordination number 8 is it is a body centered void. Is this clear? Now, we are going to do some little calculations. One thing you need to understand that these atoms, they are touching each other. These atoms are touching on each other, the body diagonal. Now this size is R minus. We are taking the anion as creating the entire lattice. This one would be R minus. And when we talk about this part, this is R plus, this is R plus. Okay? So Agatha, you are not here to study. So don't please spam. Don't spam. Okay? You are blocked. Saugata Manna John. I have taken your name to tell you that you are being blocked. Anybody find anybody disturbing? Don't answer the person, simply block them. He says that he has got selected in AIMS. Congratulations. You don't need to be here in this class. Okay, let's get further. So coordination number is equal to 8, body center void, and the person would say, क्या attitude है यार इस टीचर का? 10 बच्चे क्लास में फिर भी कह रहा है ब्लॉक कर दूंगा. But क्या करें? That is what I am. Okay. So here we have the body diagonal. So let's calculate it. So to calculate it, what we do? Body diagonal is equal to twice of r plus twice of r minus. Now body diagonal for a particle exactly fitting in the cube will also be equal to root 3a, edge length. Now a would be equal to twice of r minus. This is what we have as. This is equal to root 3 into twice of r minus. Is this clear? So now let's equate the body diagonals. We have under root 3 into twice of r minus is equal to twice of r plus twice of r minus. Here we can cancel out this twice and we are going to get root 3 r minus is equal to r plus r minus. This would mean r plus is equal to root 3 r minus r minus. So that would mean r plus is equal to root 3 minus 1 r minus, and r plus upon r minus is equal to root 3 minus 1, and that is equal to 0.732. Is it clear? So here we have actually derived the minimum size of the cation to fit in a body-centered void. Okay, so r plus must be greater than equal to 0.732 r minus to fit in cubic void. Many times the question is asked, what is the minimum size of the cation to fit in the cubic void? What would be the minimum arrangement? What would be the minimum size? So this is what we have, the arrangement. This is what we have as the size. Is it clear? Now, having talked about this, we have something called cesium chloride arrangement. the cesium chloride arrangement. What exactly is cesium chloride arrangement? Cesium chloride arrangement is the simple cubic arrangement of anion in which the cation occupies all the body centered or cubic voids. Clear? It's a simple cubic arrangement of the anion in which the cation occupies all the body centered or cubic voids. Now, this is what we call a cesium chloride arrangement. Now, when we talk about the coordination, cesium ion is going to have a coordination of 8 and chloride also is going to have a coordination of 8 because each corner of the cube is a part of 8 other cubes. So if this corner is touching one cesium ion, it's going to touch 7 other cesium ions. So its coordination would turn out to be 8. Now when we talk about the contribution, cesium occupies the body center, so its contribution is 1. Chloride occupies all the corners and each corner has a contribution of 1 by 8. So 8 corners will have a contribution of total 1. Now, one very important thing about the cesium chloride arrangement is the body diagonal is equal to twice of R plus R minus, and that's equal to twice of bond length. So if you are getting the radius of the cation and the body diagonal, you can easily find out the radius of the anion as well. So this kind of a question is generally asked. Anybody has to ask anything about the cesium chloride arrangement? Okay, once you have talked about cesium chloride arrangement, now let's get along with another arrangement. This is the cube that we have. Okay. And we place, what we do is we divide this particular into 8 smaller cubes. Okay. Now we place the particles at the specific points. This is going to be one particle. This is another one. Here we have another one. Here, here. Okay. Now this is a face-centered cube. Now let us say I place a particle right in the center of this face-centered cube. Can you tell me what is the coordination of the particle placed in the center of the face-centered cube? Tell me, what will be the coordination of the particle placed in the center of the face-centered cube? Tirthraj, I'm talking about the red particle, not every particle. The particle near to it is this. One, one, two, three, four, five, six. The coordination number of the red particle is 6. It's not 12. Do you hear the question or not? I'm talking about the coordination number of the particle placed in the center of the face-centered cube. I'm not talking about the coordination of the particles at the corners or the face center. And even if I talk about the coordination of the particles at the face center and the corner, now the coordination is not about the particle of the same type, but the particle which has been placed right in the center of the cube. Sorry, sir. What do you mean by sorry, sir? Tirthraj, you don't even listen to the question. How are you going to answer if you don't listen to the question? So this is a octahedral void. So what we can understand is the center of face-centered cubic unit cell is an octahedral void. Can you understand that? Clear? Now, let's place a particle at the edge center, the edge center. Okay. If I place the particle at the edge center, can you tell me how many particles are going to touch it? How many particles are going to touch a particle at the edge center? These are the particles from the other cube. Again, it is going to be 6 coordination. So, edge center also is a is an octahedral void. Edge center is also an octahedral void. Clear? So what we can say is for a face-centered cube, for a face-centered cube, the body center and edge center are octahedral. Okay. Now let's talk about the contribution of octahedral voids. Contribution of edge. Now you need to remember edge is shared by 4 cubes. Edge is shared by 4 cubes. Welcome Sheetal Jain, how are you? Sheetal, I believe you have got the admission in AIMS. Yes, we can expect. Afaq Bangash, welcome. I'm perfectly fine. Yes, it can be there. Matrix match type questions are there. Reason assertion type questions are there. Lot many types of questions can be asked. Sheetal, you have not yet sent me your scorecard. Tirthraj, please give Sheetal Jain my WhatsApp number so that she can send the code. And you can even share with her my Telegram link, the group. I believe she would like to send it on the group. Okay. So when we talk about the contribution of edge is 1 by 4. So number of edge is 12. A cube has 12 edges. So the total contribution becomes 1 by 4 into 12, that is equal to 3. So 3 is the contribution of the edge. Now we have something like contribution of body center. That's going to be equal to 1. So the total contribution of the octahedral voids in a face-centered cubic arrangement is 3 plus 1 equal to 4. Now, contribution of particles making the unit cell. The contribution of the particle making the unit cell is also equal to 4. Face-centered cubic arrangement. The contribution of the particles is 4. Is that clear? Sheetal Jain, send on this number on WhatsApp. There was a person who wanted to join the group, but okay. Tirthraj has already written in Priyanshu. Tirthraj has written in Priyanshu. Now you have it, Sheetal. You can send it on the WhatsApp or you can send it on the Telegram. Telegram also, this number is registered. You can find it. Okay. So that's what we have. So one thing is very clear. The number of octahedral voids. The number of octahedral voids in any close packed arrangement. The number of octahedral voids in any close packed arrangement. That could be the CCP, which we call as the face-centered cubic arrangement, and HCP, that is hexagonal close packing, is the same as number of particles present in that arrangement. Is that clear? Is this clear? So it is the same as the number of particles present in that arrangement. Now let's talk about one more thing. When we talk about this particular arrangement, what you can very well see is that here this edge length A is equal to twice of R plus twice of R minus. The edge length is equal to twice of R plus twice of R minus. Can you see that? Any confusions with that? Got it? Any confusions here? Now, now it would mean that the edge length A is equal to twice of R plus twice of R minus. Now, this is what we have as a face-centered cube. Face-centered cube says that the edge length A is equal to 2 root 2 R minus. Now, that's what we have already done. So, it is for a face-centered cube. Now, this twice of R plus twice of plus R minus would be equal to 2 root 2 R minus. Yeah. So this twice goes, and we get R plus R minus is equal to root 2 R minus. So R plus would be equal to root 2 minus 1 R minus, and R plus upon R minus is equal to root 2 minus 1 is equal to 0.414. Okay, so this is the minimum size of the cation to occupy the octahedral void. So I can say that R plus should be greater than equal to 0.414 R minus to occupy octahedral void. Arman Ali, how does it make a difference? Who is Bengali? Who is Malayali? Who is anybody? I believe they all are students, and that's the most important thing. Nothing else. Is this clear? Now let's talk about the NaCl or rock salt arrangement. The rock salt arrangement, the NaCl or the rock salt arrangement. What is NaCl or rock salt arrangement? It is the face-centered cubic arrangement of anion. Okay, it is the face-centered cubic arrangement of the anion in which cation occupies all the octahedral voids. It's a face-centered cubic arrangement of the anions in which cation occupies all the octahedral voids. And the important thing is, this part is not given in NCERT. They are asking the question based on it, but they are not explaining it in the NCERT. Is it clear? So here we have Na plus, we have the Cl minus, and we have the coordination. Coordination of the sodium ion would be 6 because it's occupying the octahedral void, and chloride also is going to be 6 because it's surrounding the sodium ion. They are in each other's octahedral void. And then we have contribution. The contribution of the octahedral void is 4, and the contribution of the particle making the arrangement is 4. And now you need to remember the edge length is 2 into bond length. So this is all about the sodium chloride arrangement, and you need to remember it. Is this clear? Any kind of confusions? Now, having talked about this, let's talk a little bit further. This is a face-centered cube. Now what I do is I take one cube out of it. Let's say this one cube. We talk about this cube. इसको थोड़ा सा हम arrange कर देते हैं. लो. We talk about this particular cube. So I talk about this particular cube and I place a particle right in the center of this cube. How many particles are going to touch this particular particle? How many particles will be touching this particular particle? That is the particle in the center of a small cube. Any doubts? Sheetal Jain, you have not yet sent your scorecard. Suhail Khan, NEET Elixir batch is going to start from 16th of August. Now, this particular particle is going to be attached to. This is coming outside. This is going inside. This is again coming outside. And this is going inside. So here, the coordination number is equal to 4. Now, if its coordination number is 4, that means this is a tetrahedral. So I can say one thing, that the center of every small cube is a tetrahedral void. Okay. Now, tetrahedral void is present on the body diagonal. 1/4 of the body diagonal, that tetrahedral void is present. 1/4 and 3/4. ठीक है? Is this clear? Anyone has to ask anything about it? So this is what we have as cesium chloride arrangement. Can you see the cesium chloride arrangement? Any confusions? So this is what we have as the octahedral and the tetrahedral void. These are the octahedral voids. Can you see them? Suhail, we have shifted it a bit more. And don't worry, these YouTube batches are continuing in which we are going to complete the course quite fast. So don't worry about it. Once we start with the plus batches, the YouTube batches have to become a little lower. Okay? So you are going to gain everything from there. Okay? So here we have the octahedral voids. Can you see them clearly? The octahedral voids. Now this is what we have as a tetrahedral void. Priyanka, just try to understand. If you have a doubt, ask me. I'll explain it again. और हिंदी में बोलने में कोई प्रॉब्लम नहीं है. द ओनली थिंग इज कि आपको अपना जो मेडिकल का जो पढ़ाई करनी है वो इंग्लिश मीडियम में होगी. तो इट इज बेटर यू स्टार्ट इट राइट नाउ. ठीक है. एंड you will be able to gain much knowledge of English as well from these sessions. Okay. बेटा नीट निकलेगा. अगर तुम्हें यह भी डाउट है कि नीट निकलेगा या नहीं निकलेगा तो फिर प्रॉब्लम क्या है? फिर तो करने का कोई जरूरत ही नहीं है. T4 Tech. बेटा यू हैव ज्वाइन द सेशन ओनली टुडे. अच्छा मार्क्स कैसे आएगा? पढ़ो. सारे के सारे जितने भी सेशंस हो चुके हैं, दे वर मैराथन सेशंस. यू हैव टू जॉइन देम एंड यू कैन गेट थ्रू देम. So that is what we have as a tetrahedral voids. So in FCC unit cell, the body center and the edge center are the octahedral voids. The number of octahedral voids in any close packed arrangement, that is hexagonal close packing. Just read through it. This is very important part. And the number of tetrahedral voids is twice this number. Because the smaller cube that we are getting are 8 in every face-centered cubic lattice. Is it clear? So that's what we have a sodium chloride arrangement. Let's do this question. Calculate the number of unit cells in a crystal of NaCl which weighs 4.85 grams. Remember, contribution in NaCl unit cell is 4Na plus and 4Cl minus. That is the same as 4NaCl formula. Solve it and give me the answer. Answer. The first thing what you need to do is find the number of sodium chloride particles. 58.5 grams NaCl has 1 mole NaCl formula units. That is 6.022 into 10 raised to power 23. Okay. So 5.85 gram is going to have 6.022 into 10 raised to power 23 divided by 58.5 multiplied by 5.85. And that's equal to 6.022 into 10 raised to power 22 NaCl. Clear? 4 NaCl give 1 unit cell. So 6.022 into 10 raised to power 22 NaCl will give 1 by 4 multiplied by 6.022 into 10 raised to power 22. Okay. Now that's equal to 1.5055 into 10 raised to power 22 unit cells. Any confusions here? Just note it down. Is this clear? Now we have the tetrahedral voids. You need to remember it. This is a very important part. Is this clear? Anybody who has not liked the session as yet, please like it. Now we are talking about the calcium fluoride arrangement. What is calcium fluoride arrangement? It is a face-centered arrangement of cation in which anion occupies all the tetrahedral voids. It's a face-centered arrangement of cation in which anion occupies all the tetrahedral voids. So here we have Ca2 plus and we have F minus. When we talk about the coordination, calcium has a coordination of 8 and fluoride has a coordination of 4. When we talk about the contribution, calcium ion has a contribution of 4 and fluoride ion has a contribution of 8, and this is the unit cell. Just note it down. Is this clear? 56 grams. Where is 56 gram as a question? Now, this is also a zirconium oxide arrangement. Zirconium oxide arrangement is the same as the calcium fluoride arrangement. So, zirconium oxide arrangement is also the calcium fluoride arrangement. ZrO2. Okay. Now, this is how the calcium fluoride arrangement looks like. Last question was the number of unit cells. Seen it? Any confusions, anybody? This is another way to view it. Clear? Anybody who has not liked the session, go ahead and like it. Chances are low. समझ में आ रहा है, दिखाई दे रहा है, क्लियर है? This is also called the fluorite arrangement. Then we have antifluorite arrangement. Now, antifluorite arrangement is sodium oxide. The only thing is the cation and anion positions are interchanged. Okay. Here, sodium occupies the tetrahedral void and oxide makes the entire arrangement. So that's what we have as sodium oxide or the antifluorite arrangement. Is it clear? And then we have zinc sulfide arrangement. Zinc sulfide arrangement is again a face-centered cubic arrangement of the sulfide ions in which zinc occupies alternate tetrahedral voids. That is, instead of 8, it is occupying only 4 of the voids. That is what we call a zinc blend or the zinc sulfide arrangement. Is it clear? So this is the zinc sulfide arrangement. So out of 8, 4 particles, 4 voids are occupied. Any confusions? Okay, have 3-minute break. We start at 12:18. 12:18 we are going to start. It is not given in NCERT, Piyush. This part is not given in NCERT. Okay, so beginner, let's begin over it. So diamond is a zinc sulfide arrangement that we need to understand. That's what we have as zinc sulfide arrangement. Now there is a little bit effect of temperature and pressure, and this is what you need to understand that if NaCl is crystallized under high pressure, it becomes a cesium chloride arrangement. And if cesium chloride is crystallized at high temperature, we get a sodium chloride arrangement. Okay? Okay? Now let's do a few questions. Now this is the example of NCRT. NCRT has not taught it, but NCRT is asking it. That's the beauty of NCRT. One fourth they have as theory, one fourth they have as examples, and the rest of it, half of it, they have as questions. And so they cover everything and do nothing. Answer. Answer. Solve it, solve it. We have the element X and element Y. Okay. X is cation occupy the octahedral void. So we have X and we have Y. Now they make the Y makes CCP. So the number of Y in a unit cell is 4. X occupy the octahedral void. The octahedral void is 4. So the formula of the compound is XY. Any confusions? Are you attempting it or you are sleeping? Clear? Just read through it. Answer is written here. I've already explained it to you, but it is written also here. Again, another question. Solve it. And this is the question from NCRT. Yes, Priyanshu, because we are only going to talk about the cubic close packing and hexagonal close packing. We are not going to talk about any other packing. So it is going to be always true. Solve this particular question. Solve it. Answer. Okay, atoms of B form HCP lattice. HCP lattice has a contribution of 6. So B is 6. And those of the element A occupies two-thirds of the tetrahedral voids. Now, tetrahedral void are double of the number of the particles, so it is going to be 2 by 3 of 12. So, this becomes A8, B6. And when you simplify it, it becomes A4, B3. Any confusions? Clear? Read through the solution. But why are you not giving me the answer? If it is clear to you, you should be giving me the answer, not waiting for me to give the answer. Do this question. Do this question. Solve this question. Solve. Oxide ions are 4. Where are the others? Solve. Yep. Now Al3 occupies half of the octahedral voids. Octahedral voids are going to be 4 and that's going to be 2. Magnesium occupies the tetrahedral voids. Since oxygen is 4, tetrahedral voids are going to be 8 and it's going to be by 8. So the formula comes out to be Mg1Al2O4. Mg Al2O4. That's the formula of spinel. Solve this question. सॉल्व MgAl2O5 नहीं है बेटा, MgAl2O4 है. I have checked it once and even twice. See, this is how we solve it. अबे गूगल, see the question and then solve it. I don't know who the heck the Google has given. Google पे ये दे रहा है. The formula is SPINEL, and you can check it on Google. It is MgAl2O4. It's a rare gemstone that was used to imitate rubies. हे राम, ये चैट जीपीटी में कुछ भी होता है ना. Solve this particular question. Solve it. अरे यार, कभी तो तुम मुझे आंसर दे दो. Do I have to give all the answers to you? We have Fe2 plus, we have Fe3 plus, and we have O. Now, O forms 4. Fe2 plus occupies one-fourth of the octahedral voids. So it is 4 by 4, while occupies Fe3 plus occupies one-eighth of the tetrahedral, that is 8 by 8, and one-fourth of the octahedral voids, that is 4 by 4. So the formula is simply Fe2 plus Fe3 plus twice O4, or normally which is written as Fe3O4. Such a simple question. Why do you take so much time? Is this clear now? Answer. Answer. That is, B forms a simple cubic arrangement. B becomes 1. A occupies all the face centers. Face centers are 6 and each has a contribution of 2, 1 half. So it becomes A3B. Getting it? I'm uploading this particular entire thing to you. Just read through it and we are going to have the discussion. Okay? I'm just uploading it. So this is how our biggest offer, 25% off on all Plus and Store subscriptions. Subscribe now using the code AVLive. Okay. Iconic Mega Sale Week is here. Again, AV Live, and this is what we have as a schedule. And you just remember it is 10 a.m. chemistry. So we are having 10 a.m. chemistry also. Join our Telegram channel for YouTube classes PDF. NEET UG subscription. Join with us. And unacademy.com/Anoop Vashishtha is my page on Unacademy. NEET Elixir by Unacademy. Thank you. Bye-bye. I'm just uploading the notes. You can go through it on the Telegram channel. Bye-bye. Good day. We are meeting at 4 p.m. with chemical